Hey, welcome to the Explainer. In differential equations, finding a solution feels like you've finally reached the finish line. But what if that solution has a secret expiration date? Today, we're diving into a really crucial and honestly often overlooked concept, the interval of validity.
So think about it. You've done all the hard work, right? You separated your variables, maybe you found an integrating factor, and boom, you landed on that beautiful function for y. But hold on, does that solution actually work for every possible value of your variable? Is it good forever? That is the big question we're going to tackle today.
And this quote, well, it hits the nail on the head. A formula for a solution is kind of like having a key. But the interval of validity is what tells you which doors that key can actually open. It defines the boundaries, the domain where your solution is actually meaningful and, exists.
So here's our game plan. First, we're going to uncover a solution's hidden rules. Then, we'll dive into the two very different worlds of linear and nonlinear equations. After that, we'll get our hands dirty with some worked examples, and finally, we'll land on the one key thing you need to take away from all this. Think of it like this. Your solution has an operating range. Yeah, just like a fancy piece of equipment. It only works under certain conditions. If you go outside that range, the solution it breaks down. It's no longer valid. All right, so here's the official definition. Now, the two super important parts here are that it has to be the largest possible interval, and this is non-negotiable. It absolutely must contain your initial condition. That starting point, your T0, that's your anchor for this whole process.
Okay, now this is where things get really, really interesting. How we find this interval, it completely changes depending on the type of differential equation we're looking at. Because you see, linear and nonlinear equations play by two totally different sets of rules. So this slide right here, this is the heart of the whole thing. For linear equations, over on the left, it's like having a map before you even start your journey. The big theorem for linear equations guarantees a single, well-behaved solution exists wherever your coefficient functions, p of t and g of t, are continuous. So all we have to do is check them for any breaks or gaps before we even think about solving. But for nonlinear equations, man, it's like you're venturing into totally uncharted territory. You can't see the dangers ahead. You have to find the actual path, the solution first, because the very nature of that path depends entirely on where you start. So why are they so incredibly different? Well, it's because nonlinear solutions can do something that a nice, predictable linear solution would never even dream of doing. They have a bit of a wild side. And there it is. They can blow up. What does that mean? It means the solution curve can just be cruising along, looking perfectly fine, and then all of a sudden it just shoots off to positive or negative infinity and poof, it just stops existing. And this isn't just some math curiosity, it actually models real stuff where things escalate really, really fast, like a chemical reaction that gets out of control. And here's the really wild part. Where the solution blows up depends completely on its initial value. A classic example we're going to look at is y prime equals y squared. With that equation, just changing your starting point literally changes the exact moment in time where the solution explodes. This crazy unpredictability, that's a hallmark of nonlinear equations. It just doesn't happen with linear ones. All right, theory is great and all, but let's see how this stuff actually works in practice. We're going to walk through a few examples, one for each kind of scenario, to make this crystal clear. Okay, first up, a linear equation. Remember the rule? We don't have to solve it. So step 1, we get it into standard form so we can clearly see our coefficient functions. Step 2, we hunt for any points of discontinuity. Here, we see problems when t is plus or minus 1, and also when t is less than or equal to 0, because of that natural log. Step 3, that gives us our list of bad points. Now for the final step, we find our initial condition, t0 equals 2 on a number line. The only continuous interval that contains our anchor point of 2 is everything from 1 to infinity. And that's it. That's our interval of validity. Done. All right, now for our nonlinear example, y prime equals y squared. The rules are totally different now. Step 1, we have to solve it. So after separating variables and doing our integration, we find the solution is y equals 1 over 1 minus t. Step 2, now we look for problems. And we can see right away the solution is undefined when t equals 1. This is our blow up in action. Step 3, our initial condition is at t0 equals 0. So the largest continuous interval that contains our starting point of 0 but avoids that disaster at t equals 1 is everything from negative infinity all the way up to 1. That's our answer. See the difference? Let's do one more linear case, this one with a little twist. Step 1, our coefficient p of t is tangent of t. Step 2, we know that tangent has discontinuities wherever its denominator, cosine of t, is 0. Step 3, as you can see, this creates this infinite series of bad points that act like walls, chopping the number line up into all these separate little intervals. So how in the world do we choose the right one? Well, step 4, we locate our initial condition, t0 equals pi. We find pi on this number line, and we can see it's trapped in that interval right between pi over 2 and 3 pi over 2. That single point locks us into our one and only one correct window of validity.
So, after all of that, what is the key takeaway? What's the one thing you really need to remember? It all boils down to one essential difference in how you approach these problems. Let's just put it all on one table to make it super clear. For linear equations, your method is to check the coefficients p of t and g of t before you solve. It's predictable. The initial condition's only job is to pick the right interval from a list of options you already know. But for nonlinear equations, you absolutely must solve the equation first. The interval is a total mystery until you see the solution, and that initial condition is actually part of what determines the interval itself. So the most important thing is, always know what type of equation you're dealing with first.
And we'll just end on this thought. Learning about the interval of validity teaches us that our answers, our solutions, they have boundaries and they have rules. And it kind of makes you wonder, doesn't it? What other hidden assumptions might be lurking in the math problems that you solve every single day? Thanks for watching.